Welcome to our electromagnetic field theory lecture series. In this lecture 13, we are going to discuss on uniqueness theorem. The objective of lecture 13 is to understand the concept of uniqueness theorem, in which we would try to calculate electric potential and electric field at a given point using the solutions of either Poisson's or Laplace equations. In our previous lectures, we have tried to calculate electric field intensity using different approaches. If we know the charge distribution for a given setting, we can calculate electric field based on Coulomb's law and Gauss' law. From charge distribution, we can also calculate the potential difference. The electrical potential difference can also be used to calculate electric field using potential gradient. In this lecture, we are going to look at an approach based on uniqueness theorem. Uniqueness theorem is based on area properties and boundary conditions for a given setting. The solution for an electrostatic problem can be unique for a given setting. If supposedly our approaches satisfy boundary conditions when using either Poisson's or Laplace equation, we can say that our approach is straightforwardly unique for the specified region. Let's recall the Maxwell equation del dot D equivalent to rho v. We are going to use this relation to derive our Laplace and Poisson's equation. For Maxwell equation, del dot D is also equivalent to del dot epsilon E, equivalent to rho v. The epsilon, being a constant, can be changed to become epsilon del dot E, equivalent to rho v. This is considering we are dealing with homogeneous material. E, based on potential gradient, is also equivalent to negative del V. If we are to bring the negative sign to the right hand side of the equation, and the epsilon to be the denominator of the right hand side equation, we would get del square V is equivalent to negative rho V epsilon. Del square V is the Laplacian operator, which would be described later. Laplacian operator is coordinate dependent. In the presence of density charge, del square V is valid. This is known as Poisson's equation. In the absence of rho V or density charge, del square V is equivalent to 0. This is known as Laplace equation. We are in need to determine electric potential based on either Laplace and Poisson equation. Let's suppose we are going to analyze on Laplace equation. Del square V, when expanded, is equivalent to the equation shown in front. This is a case of three-dimension problem using our Laplacian operator. However, in many cases, we can say that one-dimensional problem or one-dimensional Laplacian operations is also sufficient to be used. It is less complicated and much easier to be processed. A one-dimensional problem involves either this del square V over dx square, or this del square V over del y square, or del square V over del z square. For the sake of our analysis, we are going to use del square V over del x square equivalent to 0. In order to determine our V, we need to perform integration to this mathematical relation. Performing the first integration would bring us to this relation, with A being and the integration constant. Performing the second integration, we would get V is equivalent to AX plus B, with B also being the integration constant. Both A and B can be solved using boundary conditions. The steps in uniqueness theorem is to first identify whether our problem requires the use of Poisson's or Laplace equation. Then we will attempt to find V using boundary conditions. From our V, we can obtain either E, D or J based on the given problem. Finally, we can also determine charge or Q if needed. The Laplacian operator, when expanded based on different coordinate systems, are shown in front. In using Poisson's or Laplace equation, we may also use the gradient operator that are shown in front. Let's look at an example question using uniqueness theorem. Supposedly we have a semiconductor-based p-n junction transistor that has a permittivity of epsilon and a charge distribution in the depletion region defined by rho v is equivalent to rho naught in the region where x is between 0 and a. And rho v is equivalent to negative rho naught when x is between negative a and 0. In this region, we call it as type P part of the transistor, and this is type N part of the transistor. Given that electric field intensity is equivalent to 0 at x equivalent to negative a and a, plus the potential at x is equivalent to 0, we are in need to determine potential across the depletion region. The depletion region is therefore between negative a and a. So how do we solve this problem? Let's recall the information provided to us include the definition of rho v in region between 0 to a, that is rho naught, and between negative a to 0, that is negative rho naught, the value of potential at x equivalent to 0, and the value of electric field intensity at x equivalent to negative a and a, which are also equivalent to 0. To solve this problem, let's analyze first the type P part of this transistor. We are going to focus on the region in between negative a and 0. Given that this is a case where density charge is present, we can use del square V is equivalent to negative rho v over epsilon, the Poisson equation. Given that rho v is equivalent to negative rho naught, negative rho naught would become positive rho naught divided by epsilon. Del square v is equivalent to d square v over dx square. This is based on the Cartesian coordinate for x axis. Equated it to rho naught divided by epsilon. Integrate both left hand side and right hand side once, we will get dv divided by dx equivalent to rho naught x divided by epsilon plus a, the integration constant. So how do we determine our a? We will use boundary condition. When x is equivalent to negative a, we know that a is equivalent to 0. Another way to find our v is when v is equivalent to the integration of negative e dot dl. Given that dl is in x direction, it will be dx. We can rearrange or transform the relation such that it becomes dv over dx is equivalent to negative e. Putting a being 0 based on x equivalent to negative a, and putting x in this rho naught x divided by epsilon term, we would get negative rho naught a divided by epsilon plus a is equivalent to 0. A is therefore equivalent to rho naught a divided by epsilon. Now that we have obtained our a, let's insert this value into equation 1. Inserting this value of a into equation 1 would bring us this relation. If we are to perform another integration process, we will get v is equivalent to rho naught x squared divided by 2 epsilon plus rho naught a divided by epsilon x plus b, that which we will note it as equation 2. So let's try to solve the value of b. We would use boundary condition again. When x is equivalent to 0, v is equivalent to 0. Let's put this value into equation 2. X and v to be equivalent to 0. We would get v is equivalent to 0, which is equivalent to b. Therefore, this b value can be ignored. And therefore, our potential in the type P part of the transistor is equivalent to rho naught x squared divided by 2 epsilon plus rho naught a divided by epsilon x, which is also equivalent to these terms shown on the slide. This is for the region where x is between negative a and 0. When solving for region when x is between 0 and a, we would get the potential for type N part of the transistor equivalent to rho naught divided by epsilon in bracket Ex minus x squared divided by 2. Now that we have obtained potential at the type N and type P parts of the transistor, we can get potential across the depletion region, which is across when x is equivalent to negative a and a. The potential difference between these 2 points can be obtained if we are to put in the value of x at these 2 points based on our knowledge of this part of boundary of the depletion region. When trying to find the potential difference, we would try to obtain the potential at this point over here, that is when x is equivalent to a. When x is equivalent to a, putting x equivalent to a here, and A squared to be here, we would get rho naught divided by epsilon, multiply it with A squared divided by 2. Hence, this term here. The potential at x equivalent to negative A is equivalent to these mathematical terms with the x replaced by negative A. As such, we would eventually get the terms to be negative rho naught A squared divided by 2 epsilon. So the potential obtained earlier minus the potential here, we would get potential difference between these two points at the edge of the depletion region. Eventually, we will get V is equivalent to rho naught A squared divided by epsilon V. This is just an example question of our Poisson equation. With that, we have reached the end of electrostatic topics. In our next lecture, we are going to look into magnetostatic. Thank you.